Welcome back, calculus students. We are continuing to work on 4.2, which is area with summations, and the fundamental theorem of calculus, which is actually 4.4. If you are in my calculus class and you are watching this video as an assignment, then I do expect you to have these examples written in your notebook. Otherwise, simply enjoy and learn a little bit, hopefully. So example 2 here. Use the limit process to determine the area of the region bounded by f of x equals 4x squared plus 2x minus 5, x equals 2, x equals 11, and y equals 0. Hopefully you know y equals 0 is simply the x-axis. Okay, we need to just talk about this function for a quick moment here. 4x squared plus 2x minus 5. If you evaluate that function at x equals 2, you're going to end up with 15. The point 2 comma 15 is on that graph. And if you evaluate the function at x equals 11, you're going to end up with 501. So the point 11 comma 501 is on this graph. This function is monotonic on the interval between 2 and 11, and the function is strictly increasing. So monotonic means either strictly increasing or strictly decreasing. This function is definitely not only monotonic and increasing, but everything's positive. So doing this limit process is going to be just fine for us. Okay? All right, well, in order to start our limit process, we have to look and see what our delta x is going to be. Our delta x has a formula. Delta x is equal to b minus a divided by n. We have the interval here from 2 to 11, which means that our a is 2 and our b is 11. So my delta x is going to equal 11 minus 2 divided by n. That gives me, plain and simple, 9 over n. I need now my c sub I, because I'm going to set this thing up so that we can have the limit as n approaches infinity of the summation as I goes from 1 to n of f of c sub I delta x. So I need my c sub I. C sub I is a plus I delta x. Since I know my a as a 2 and I know my delta x is 9 over n, I now know that my c sub I can be written as 2 plus 9i divided by n. And that's really going to help me with my delta x. Okay, I'm just going to rewrite my function here. F of x equals 4x squared plus 2x minus 5. These three pieces of information right here that we have, the delta x equals 9 over n, the c sub I equals 2 plus 9i over n, and the function itself, f of x equals 4x squared plus 2x minus 5, are going to piece together and make up my limit process that the question is asking me to use. So here we go. I am looking for the limit as n approaches infinity of the summation as I goes from 1 to n of, big brackets, f of c sub I delta x. And I'm going to fill everything in here. We are looking at the limit as n approaches infinity of the summation as I goes from 1 to n of f of, my c sub I is right up here in the middle, 2 plus 9i over n. And then my delta x is 9 over n, and I'm done with that. A little time sign in there makes it look nice. Okay, now the 9 over n is going to be pulled out in front of the summation as one of my properties that I'm allowed to use. The limit as n approaches infinity of 9 over n, I'm going to write this over here, multiplied by the summation as I goes from 1 to n. And now I need to evaluate the function f using 2 plus 9i over n. Now the function f comes from way up here. I got to bring this down into play. So 4 times something quantity squared plus 2 times something minus 5. Close my bracket. That something is my c sub I. So inside each set of parentheses here in the brackets, I need to write 2 plus 9i over n, 2 plus 9i over n. And it's just a matter of a lot of calculations, couple formulas, and cleaning everything all up. So this gives me the limit as n approaches infinity of 9 over n. You may leave parentheses around it. You don't have to have parentheses around it. Sometimes I do, sometimes I don't. The summation as I goes from 1 to n. And now I want to take care of this square here first, which means I have a binomial to square. My 4 is going to be on the outside. And when I square 2 plus 9i over n, 2 squared is 4. 2 times 9i over n is 18i over n. And I'm going to have two of those terms that are identical, so that's going to yield me 36i over n. And then plus 9i over n multiplied by itself, 9i over n, gives me 81i squared over n squared. Close my parentheses. I'm now going to distribute the 2 inside the 2 plus 9i over n and get 4 plus 18i over n, and still minus 5 on the end there. Okay, let's break this down a little bit more, clean this up. Just copying this piece. This is still the summation as I goes from 1 to n. I need to distribute my 4 and combine like terms. So 2 steps here. 4 times 4 is going to give me 16. 4 times 36 is 144. So we have I over n. Plus 81 times 4 is 324. I squared over n squared. Plus, let's see, I could do the 4 minus 5. Let me just copy that for right this second. Plus 18i over n, and then minus 5. And we'll put everything together as like terms. Limit as n approaches infinity, 9 over n. The summation as I tends to 1, goes from 1 to n. And let's see here. We have 16 plus 4 is 20, minus 5 is 15. I have 144i over n, and then I have 18i over n. That's going to give me 162i over n. I'm going to put the n here and the I right there. And then I'm simply going to write 324 over n squared and write the I squared separately. All right, so far so good, I hope. Okay, let's split this thing up here and take our time at this. This gives me the limit as n approaches infinity of 9 over n. And now I'm going to break this sucker up here. Big bracket. This is the summation as I goes from 1 to n of just 15. Plus, I'm going to take this 162 over n and I'm going to write it on the outside of my summation. And now I have the summation as I goes from 1 to n of simply I, which is nice because this is just a formula I can evaluate in the next step. Plus, once again, the 324 over n squared is going to be written on the outside, 324 divided by n squared, times the summation as I goes from 1 to n of I squared, which is another one of my formulas. So now it's time to implement the formulas. The limit as n approaches infinity, 9 over n, big bracket. So I have the constant formula here, which says the summation as I goes from 1 to n of a constant is that constant itself multiplied by n. That's what I get out of that. Plus 162 over n. And this right here is a formula that says we have n times n plus 1 all divided by 2. And I'm going to copy the 324 divided by n squared. This is another formula. The summation as I goes from 1 to n of I squared is n times m plus 1 times 2n plus 1 all divided by 6. Close my bracket. And this is multiplication in between each of those fractions. Alrighty. Let's continue on. Simplify down. I will rewrite my limit as n approaches infinity. I think I would like to just copy the 9 over n. There's a lot going on inside these brackets, so I'm going to clean this up a little bit before I distribute the 9 over n inside the brackets. This is just 15n plus, let's see, n divides by n once, n divided by n once, 2 divides by 2 once, and 2 divides into 162 81 times. So this is just going to give me, let's see here, 81 multiplied by n plus 1, all divided by 1, so I don't have to worry really too much about that. And then plus, let's see, 6 is going to divide into 324. 6 goes into 6 once, and 6 goes into 324 54 times. And then this n right here can divide into itself, divides into n squared, just giving me n down here. So let's see, I will end up with an n on my denominator, and on my numerator I simply have 54 times n plus 1 times 2n plus 1. Close my bracket. Everything should look okay. Equals the limit now as n approaches infinity. I now need to multiply the 9 over n through by each and every one of my 3 terms inside the brackets. So I have, I'm going to just write this out nice and clear so nobody has any questions. 9 over n multiplied by 15n plus 9 over n multiplied by 81 times n plus 1 plus 9 over n multiplied by this fraction which has 54 times n plus 1 times 2n plus 1 all divided by n. And I have to clean that up. Limit as n approaches infinity. We have this n right here. Whoops, this n divides into this n, giving you 1 and 1. And 9 times 15 is 135. Plus. Now 9 times 81 is 729. N plus 1 over n. Plus, see, I can't cancel anything else out here either. So 54 times 9 is going to be 486, n plus 1, 2n plus 1, all divided by n squared. Alrighty, I am ready to take the limit. Now I could rewrite this and I could say, you know I will, just to make sure everybody's clear on things. The limit as n approaches infinity, let me come back up here and make that n look nicer, right there too, of simply 135 plus the limit as n approaches infinity of this big thing here, 729 times n plus 1 divided by n plus the limit as n approaches infinity of this big thing here, 486 times n plus 1 times 2n plus 1 all over n squared. So I'm really going to take the limit as n approaches infinity 3 times because I had 3 terms. Now, to be honest with you, I would have skipped that step and gone straight to my answer, so if you do so, I'm okay with that too. The limit as n approaches infinity of 135 is just 135. And then plus the limit as n approaches infinity of what's in these brackets right here. This is a rational function because I have a polynomial function on the numerator and a polynomial function on the denominator. The degree of the numerator is 1, the degree of the denominator is 1, and since I'm asking for the limit as n approaches infinity, I'm really asking for the far end behavior of this graph, which is describing any horizontal asymptotes that this rational function might have. So I need to take the leading coefficient on my numerator, which is just 729, and the leading coefficient on my denominator, which is just 1. Let's go back here, sorry. And I need to take the ratio of the leading coefficients. 729 compared to 1 is just 729. Now I take the ratio of the leading coefficients because the degree of the numerator was equal to the degree of the denominator. This 1 right here is equal to this 1 right here, and therefore that's the process of finding any horizontal asymptotes as you compare the leading coefficients. Alrighty. You also have to recognize that as you're taking the limit as n approaches infinity, you're actually asking for horizontal asymptotes. So that connection needs to be made in your mind as well. So plus. Now I have this polynomial function here on the numerator. I have a polynomial function on the denominator. The degree of my numerator, let's see, the degree is a 1 here, and a 1 here. My exponents are 1 and 1, so the degree of my numerator is a 2. The degree of my denominator is a 2. I can see that clearly because I have n squared. Again, I need to take the ratio of the leading coefficients. Now, this is not in the standard polynomial expanded form, but if it were, I would be multiplying 486 times 2. 486 times 2 is 972. I would be comparing that with the leading coefficient on my denominator, which is a 1. So 486 times 2, like I said, is 972. Compare that to 1, it's just 972. I add these numbers all up, 135 plus 729 plus 972, and my answer is 1,836 for a final answer. That ends up being the number of squared units contained in the region, bounded by, let's go back up here, the function f of x equals 4x squared plus 2x minus 5. The vertical line x equals 2, the vertical line x equals 11, and y equals 0, which is a horizontal line. It's the x-axis. So I ended up with a region up in quadrant 1 that had an area of 1,836. I'm going to take my function notation back. Let's get this. Let's see if I can grab all of this from here to here. Actually, I don't need all that. Let's just grab my function notation again. Okay, and we will copy that down here. There we go. Here's my function. I am looking at the interval between 2 and 11, so from 2 to 11, and I want that area bounded from that graph, x equals 2, x equals 11, and the x-axis. That is known as your definite integral between 2 and 11, 4x squared plus 2x minus 5 with respect to x. So we're going to integrate this thing and apply the fundamental theorem of calculus. So let's get busy on this. Let me see. When I multiply 4 times the integral of x squared, that's x cubed over 3, I get 4x cubed over 3. Plus 2 times x squared over 2 minus 5 times x. That's what you get when you take the antiderivative or the integral of your f of x, and we're going to evaluate that from 2 to 11. Alright, big bracket, clean it up as you go along, okay? 4/3 times something cubed plus, notice my 2's will divide off, okay, so I just have something squared minus 5 times something, close my bracket, minus, big bracket, copy everything you just did again, make sure all exponents are copied accurately. I know that's my fault every once in a while. It's where I make mistakes as I copy my exponents wrong. So I should be cubed and squared and nothing, cubed, squared, nothing, everything looks good. What goes into my parentheses in the first set of brackets? You should be saying your upper limit, which is 11. So you write 11 all the way through those parentheses. And your lower limit goes into the second set of brackets everywhere you see a set of parentheses. And now we evaluate this. Clean up inside your parentheses, your brackets first, please. 11 cubed. Well, 11 squared is 121. You multiply 121 by 11 again, and you get 1,331. Plus 11 squared, I just said was 121, and then minus 55. Close your bracket. Open bracket. Copy my 4/3. Not really liking that 4, so I'll redo that. 2 cubed is 8, plus 2 cubed is 4. 5 times 2 is 10. Let's clean this up a little bit, as much as we can. Definitely, let's see, 1,331 doesn't divide by 3 because it was created by 11 times 11 times 11, and 11 doesn't divide by 3, so therefore its cube won't divide by 3. I'm going to multiply that out and get 5,324 plus 66, because a positive 121 minus 55 yields you with a positive 66. This will give me 32 over 3 minus 6. Very nice. Now I'm thinking maybe I'll make a common denominator and put these things together, Another part of me says, no, go ahead and distribute and see what you get. Maybe everything will work out without having to divide too much and making common denominators. So that's what I'm going to do. I'm going to say 5,324 over 3 plus 66 minus 32 over 3. And now minus my negative 6 will give me a plus 6. That's going to work out kind of nice. Let's see. I'm going to just move things around a little bit. 5,324 over 3 minus 32 over 3 plus 66 plus 6. And I know you probably could have moved those in your head and done this anyway, but I end up with 5,292. Let me see, 5,292. You can go to the side and do this. 5, 3, 2, 4, take away 32, and you end up with 2. You borrow here, that makes it 12, you get 9. Okay, so 5,292 thirds plus, and 66 plus 6, I don't think we need the side for that, that's just 72. So I do this division. I take 5,292, divide by 3. Now actually before I did that, I added the digits, 5 plus 2 plus 9 plus 2, and I ended up getting, what's that, 7, 8, 9, 18. And 18 divides by 3, so I know this answer is going to divide by 3 just nice and give me a whole number with no leftover remainder. So this is going to give me 1,764 plus 72. Add those up, and that ends up with 1,836 for my final answer. And I go back up to the beginning, and let's see if this checks. Did I have that same number? I don't even remember. Look at that. 1,836 was my final answer by doing the long limit process. I come down here, 1,836 is my final answer simply by recognizing my function and my upper and lower limits, integrating and applying the fundamental theorem of calculus. So a little bit faster. And if you had a graphing calculator, either way would be super fast because there's ways to plug both of these things into a graphing calculator and get the same answer. Okay, so challenge yourself maybe to take this first statement that we wrote here. Where am I? Take this first statement that we wrote, this right here. Challenge yourself to take this, come up with your function f of x and your closed interval from a to b for which you're finding the area bounded by. Okay, that would be another good question that you could have. I can't ask you that question because I already gave you that information way back in the beginning, but you could double check, see if you can figure it out. Okay, 2 different ways to work the same problem. We will end this video and say once again, talent out. Bye, you guys.